After studying the module, you will be able to understand the unit root stochastic process in detail. Also, other processes like ARMA, ARIMA, which generate time series, the phenomena of spurious regression. So let us try to understand the process of time series generation. We begin with unit root stochastic process. Let us assume a simple model denoted as yt is equal to beta yt minus 1 plus mu t. Let us define it as our first equation. The mentioned model is the first order autoregressive model, that is with a lag of one time period. If in this case beta is equal to 1, then the problem of unit root arises in the model, leading to non-stationarity of the series. Therefore, a unit root process is so called because the value of the estimator of the first order autoregressive model becomes equal to 1. If, however, modulus beta is less than or equal to 1, that is, if the absolute value of beta is less than 1, then the time series yt is stationary. Let us understand the characteristics of unit root process. Shocks to a unit root process are permanent in nature and would not be eliminated even if the series takes into consideration or the series as we look at it is converted into a stationary series. Also, a unit root process has a variance diverging to infinity. Let's understand the autoregressive process and discuss about it. The next type of process generating time series is the autoregressive process. Any series is said to be generated by an autoregressive process if it is defined as yt equal to beta yt minus 1 plus mu t. This mentioned model is the autoregressive model of order 1 denoted as AR1. This is so because we include one lag term of our endogenous variable yt, which is our yt minus 1. One important point to note here is that if beta is equal to 1, then the series becomes a random walk process or a unit root process as explained earlier. A series is generated by autoregressive process of order p, that is ARP, if we can denote yt as equal to beta 1 yt minus 1 plus beta 2 yt minus 2, so on up to beta p yt minus p plus mu t. In general term, we can define autoregressive processes as stochastic processes used to estimate the future values using the weighted sum of the past values. An autoregressive process assumes that the past values have an effect on the present values. Therefore, AR1 implies that the present value is based on the immediate past value, and AR2 implies that the present value is based on the past two values. A series is said to be generated by moving average if it is defined as under, which is yt is equal to mu t plus gamma 1 mu t minus 1 plus gamma 2 mu t minus 2, so on till gamma q mu t minus q, which is moving average model, is different from the autoregressive model in the sense that in the moving average model, the error term is regressed on the series, while in the autoregressive model, the regression is done on the lagged values of the endogenous variable. Therefore, a moving average process is the sum of random shocks or error terms. Let us now discuss and try to learn the differences between autoregressive model and moving average model in more details in this section 4.1. So we have the autoregressive models and moving average model. The difference is in the first model, regression is done on the lagged values of the endogenous variable, whereas in the moving average model, regression is done on the lagged values of the error terms. In AR model, the model is stochastic in nature, whereas MA model is deterministic in nature. Whereas the AR model can be written as yt equal to beta 1, yt minus 1, so on, till beta p, yt minus p plus mu t. Our MA model is written as yt equal to mu t plus gamma 1 mu t minus 1, so on, till gamma q mu t minus q. So I hope you can look at the differences in these two models and appreciate these differences. Let's look at the extension of AR model known as the ARMA model or autoregressive moving average model in this section 5. A series is said to be generated by the process of autoregressive moving average process, which means a combination of both, if it is defined as follows, which is that yt is equal to beta 1 yt minus 1 plus beta 2 yt minus 2, so on till beta p yt minus p plus mu t plus gamma 1 mu t minus 1 plus gamma 2 mu t minus 2, so on up to gamma q mu t minus q. So I am sure you can see we have the both combination of autoregressive model of order p, which is ARP, and moving average model of order q, MAQ. Therefore, the general ARMA model, which was first described by Peter Whittle in his thesis in 1951, is a combination of both of them. He used mathematical analysis like Laurent series and Fourier analysis with some statistical inference to explain ARMA models. It was further popularized by George E.P. Box and Jenkins in their book in 1971, also introducing a method named after them known as Box-Jenkins method for choosing and estimating the ARMA models. So the process of autoregressive moving average model can be summarized as ARP, which is, as we defined earlier, is yt equal to beta 1 yt minus 1, so on till beta p yt minus p plus mu t. We have MAQ, which is yt equal to mu t plus gamma 1 mu t minus 1 plus gamma 2 mu t minus 2, so on till gamma q mu t minus q. And we have also defined now ARMA PQ, which is nothing but a combination of these two and is written as yt equal to beta 1 yt minus 1 plus beta 2 yt minus 2, so on till beta p yt minus p plus mu t plus gamma 1 mu t minus 1, so on till gamma q mu t minus q. Let's now try to understand and learn about the extension of this ARMA model known as ARIMA model, which is in our section 6. And the full form of this ARIMA is autoregressive integrated moving average. So we have introduced the word integrated. Let us try to see what is this integration. If we difference a time series d times to make it stationary and then apply ARMA PQ model to it, then we say that the original time series is ARIMA P, D, Q. That is, it is an autoregressive integrated moving average time series where P denotes number of AR terms, D the number of times the series has to be differenced before it becomes stationary, and Q the number of MA terms. Let us discuss some of the properties of an integrated stochastic process. Let us discuss some properties of an integrated stochastic process. So we have in this section integrated stochastic process. Suppose we have a random walk process like the one defined earlier and is defined below, which is yt is equal to yt minus 1 plus mu t, and call it as equation 3. So as we had discussed earlier, that in a random walk model, the error term is a white noise term with mean equal to 0 and variance is constant in nature. It is mathematically expressed as follows, that mu t is distributed as IID normally with mean 0, variance sigma square, where IID is independently and identically distributed. So we can say that mu t is distributed independently and identically with normally with mean 0 and sigma square as constant variance. So n stands for normal distribution and 0 for mean and sigma square for constant variance. Coming back to the random walk process as expressed in equation 3, if we take the first difference, we get yt minus 1 is equal to mu t. This implies that delta yt is equal to mu t, or in simple words, we can define the first order difference to be approximately equal to the white noise. Thus, we can say that sigma yt is approximately equal to white noise. Therefore, a series is said to be integrated of order 1 if the first difference is the white noise. Similarly, a series would be said to be integrated of order 2 if the second difference is approximately equal to the white noise, and so on. Thus, in general terms, any series is said to be integrated of order d if the dth difference is the white noise. Let's look at the properties of the integrated series. The following are the properties of the integrated series which must be noted. Let us assume 3 time series, that is xt, yt and zt. The first is, if xt is integrated of order 0, that is xt is distributed as I0, which is stationary, and yt is integrated of order 1, that is yt is distributed as I1, which is non-stationary, then their sum will be integrated of order 1 and will be non-stationary time series. That is, xt plus yt is distributed as I1. This is followed from a property that the sum of a stationary and a non-stationary time series always leads to a non-stationary time series. The second property is, if xt is integrated of order d, that is xt is id, then zt, which is a linear function and is equal to a plus b xt, where a and b are constants, will also be integrated of order d. That is, zt would also be integrated of order d and can be written as id. Therefore, what we are saying is that the status of the series is not affected as far as integration is concerned by multiplying or adding any constants to the series like a and b, which we have used in our example. The third property, and an important property, is that if xt is integrated of order d1, that is xt can be written as id1, and yt is integrated of order d2, that is yt is id2, and d1 is less than d2, then zt, which is a combination of xt and yt and is equal to axt plus byt, would be integrated of order d2. This, in simple words, implies that the series containing a combination of 2 time series will be integrated of the higher order amongst the 2. The fourth property is that if xt is integrated of order d, that is xt is equal to id, and yt is also integrated of order d, that is yt is id, then zt, which is equal to axt plus byt, would be integrated as id star, where d star is less than or equal to d. Usually it is equivalent to d only, however in some cases it becomes less than d. The properties of integrated series can be therefore summed up as in this diagram, you can see we have written them in a summary form that xt if is I0 and yt is I1, then xt plus yt will be equal to I1. xt is equal to id, then zt equal to a plus bxt will also be equal to id. Similarly, if xt is equal to id1 and yt is equal to id2 and d1 is less than d2, then zt, which is axt plus byt, will be integrated to id2. And in the end, or the last property is, we have mentioned that xt if is equal to id and yt is also equal to id, then zt, which is axt plus byt, will be integrated to d star, where d star may be less than or equal to d. Let's, students, now move on and try to understand this famous Box-Jenkins or BJ methodology for ARIMA modeling. The Box-Jenkins or BJ methodology is basically used for forecasting a time series. It is based on the assumption that the time series under study is stationary or can be made stationary by differencing it one or more times. In order to determine the appropriate model, the BJ methodology follows a 4-step procedure. The first step is the identification, which means determine the appropriate values of P, D, and Q. The main tools in this search are the correlogram and partial correlogram. The second step is the estimation. Once we identify the model, the next step is to estimate the parameters of the chosen model. In some cases, we can use OLS or ordinary least squares, but in some cases, we have to resort to nonlinear estimation methods. The third step, students, is diagnostic checking. One simple test to see if we have chosen the correct ARIMA model is to see if the residuals from the fitted model are white noise. If they are, then we can accept the model. But if they are not, we will have to start afresh. That is why the BJ methodology is an iterative process. The last or the fourth step is the forecasting. The ultimate test of a successful ARIMA model lies in its forecasting performances within the sample period as well as the outside the sample period. That we will discuss at an appropriate time. Understand the phenomena or phenomenon of spurious regression. The phenomenon of spurious regression was first discovered by Yule. He stated that the spurious regression could persist in non-stationary time series even when the sample size taken into consideration is very large. The spurious regression could be judged from the value of Durbin-Watson test, whose D value is extremely low, suggesting a very strong first-order autocorrelation. So we can show it here with the help of a simple diagram where we are saying if D value is low, strong first-order autocorrelation is an indication which could hint at spurious regression results. The second method of judging the spurious regression was suggested by Granger and Newbold. They applied a rule of thumb that if R square is greater than D, then the estimated regression is a spurious regression. So we are saying that if R square is greater than D, then we have the likelihood of spurious regression, where R square is the coefficient of determination from regression and D is the Durbin-Watson statistics. Therefore, one should be extremely careful while conducting a regression test on a time series phenomenon, especially the ones exhibiting the stochastic trends. Here are some examples of spurious regressions. Egyptian infant mortality rate regressed on gross aggregate income of American farmers and total Hundaran money supply. Now, which means we have taken mortality rate of a country X, which is Egypt in this case, and income of some other farmers in America and the money supply in a third country. The total crime rates in the US regressed on life expectancy in South Africa. So if you take US crime rate and try to regress it on life expectancy in another country, South Africa, we may have some regression, some coefficients, but they may be spurious. Similarly, one can have lots of examples like India defense expenditure regressed on population of US, or population of India regressed on total R&D expenditure in the US. So which means we have country A and some parameters of country B. We can also have the number of live births in Maharashtra regressed on population of Bihar. So in all of these examples, there is no logical reason for the observed relationship among the variables. But since we have the data in quantitative terms, therefore, we are likely to end up with some regressions which have no logical reason. Hence, these are spurious regressions. We have learned in this module about the unit root stochastic process, which has been denoted as yt equal to beta yt minus 1 plus mu t. This model is basically a first order autoregressive model with a lag of one time period. In this model, if the value of beta is equal to 1, then we have learned that it will be a unit root process, because it will lead to non-stationarity of the series. However, if beta modulus is less than or equal to 1, that is, if the absolute value of beta is less than 1, then we have learned that we can call such a series as a stationary series, which means yt in that case is a stationary series. We have also learned about the characteristics of the unit root process, where we have said a unit root process has a variance which may diverge to infinity. We have different types of models which we have learned. The one very important one is autoregressive process. In autoregressive process, we have said a series is generated by an autoregressive process if it is defined as yt equal to beta yt minus 1 plus mu t. This series is of the order 1 and therefore is denoted as AR1. However, this series can be extended and we may have autoregressive process of order p, which could be denoted as ARP. I am sure you would recall how we have seen that this series can be expressed as yt equal to beta 1 yt minus 1 plus beta 2 yt minus 2, so on till beta p yt minus p plus mu t, and we have defined this process as ARP, which is very important, and the order is p. We have also learned about the moving average series or a moving average process, and we have learned that a series is said to be generated by moving average if it is defined as yt equal to mu t plus gamma 1 mu t minus 1 plus gamma 2 mu t minus 2, so on till gamma q mu t minus q, and this is denoted as MAQ, where the order of moving average is q. I am sure you can also recall and appreciate that we have tried to distinguish between the autoregressive model and moving average model. Whereas we have seen that autoregressive models are basically the lagged values of endogenous variables, which means the regression is done on the lagged values of endogenous variables. In the case of moving average models, regression is done on the lagged values of the error terms. The second difference which we have learned is that a AR model is basically stochastic in nature, whereas the moving average model is mainly deterministic in nature. And while AR1 model is expressed where yt is a function of yt minus 1 to yt minus p, and the moving average model is expressed as yt as a function of mu t minus 1 so on till mu t minus q. Also, we have learned that how these two models can be combined together to make a new model known as ARMA model, which stands for autoregressive moving average model. In this model, we have defined yt equal to beta 1 yt minus 1 plus beta 2 yt minus 2 till beta p yt minus p plus mu t plus gamma 1 mu t minus 1 so on till gamma q mu t minus q. I am sure you know we have also tried to explain this, and we have said in this the order of autoregression is p and the order of moving average is q. That is why we call it of the order pq. We have also learned that how the ARMA model was first described by Peter Whittle in his thesis, and later on it was further popularized by Box-Jenkins in 1971, and that is why by and large this model is named after them and is known as Box-Jenkins method for choosing and estimating the ARMA models. The models can be summarized, and we have summarized them in our slides earlier. Let's also try to recall how we have learned about an extension of this ARMA model in the form of ARIMA model. ARIMA stands for autoregressive integrated moving average. Whereas ARMA had two orders p and q, in our ARIMA model we also have a third dimension which is d, and this stands for the degree of integration. So, p stands for AR terms, d stands for the number of times the series has been differenced or the degree of integration or differentiation, and q is the number of MA terms. So, our integrated process also we have learned, where we have said that yt is equal to yt minus 1 plus mu t, and this mu t we have said is basically identically and independently distributed, or IID, with the normal distribution having mean equal to 0 and variance is equal to sigma square, which means it is constant. Now, if you look at the random walk process, we have also explained that how random walk process can be expressed in the form of yt minus 1 equal to mu t, which is nothing but the first difference of the earlier equation. And this therefore implies that delta yt is equal to mu t. This is what we have learned. And therefore, we can say that we have learned that how this delta yt is basically a white noise, because mu t is white noise, therefore, delta yt is also white noise. Similarly, we can have a integration of order 2, because this was integration of order 1, if we have the second difference which is approximately equal to white noise and so on, and it can be expressed as delta square yt. We have some certain properties which we have learned of these integrated series. Let me quickly repeat some of these important properties which we have learned. We have learned that if xt is integrated of order 0, that is xt is I0, which is stationary, and yt is integrated of order 1, that is yt is I1, which is known as stationary, then their sum will be integrated of order 1. Their sum will be integrated of order 1 and will be in non-stationary time series. I am sure you can recollect, we said it can be written as xt plus yt is of the order I1. Another important property we have learned, which could also be defined as the second property, is that if xt is integrated of order d, that is xt is id, then zt, which is a linear function of xt written as a plus b xt, will also be integrated of the order d. So, zt will also be integrated id. Similarly, we have learned if xt is id1 and yt is id2 and d1 is less than d2, then any combination of xt and yt, let us say zt, will be of the order d2. So, zt can be written as axt plus byt of the order d2. And let me remind you again that we have assumed that d1 is less than d2 or d2 is greater than d1. Another important property which we have learnt is that if xt is integrated of order d, that is xt is id and yt is also id, then zt, which could be axt plus byt, will be integrated of order d star, where d star has to be less than or equal to d. So, usually it is equivalent to d only, however, in some cases it becomes less than d. Another important thing which we have learnt so far is about the phenomena of spurious regression, where we have seen that how we may have spurious regression, and what we have said is if d value is low, then we may have strong first order autocorrelation and it could lead to spurious regression results. The another method which we have learnt of judging the spurious regression was suggested by Granger and Newbold, where we have learnt about a rule of thumb which says that if r square is greater than d, then the estimated regression is a spurious regression. So, I hope you can recall all these things which we have learned in this module. Thank you very much.